Hello, this podcast is on rotational kinematics. Specifically, we're going to take a look at rotational inertia, both conceptually and quantitatively, and then we'll look at rotational kinematics, once again conceptually and quantitatively. So let's take a look at rotational inertia. It's the resistance of an object to changes in its state of motion. In other words, it measures how hard it is to get an object to spin, also known as rotate, faster or slower. For instance, which tire do you think is easier to get rolling? And once it's rolling, which one's easier to stop rolling? Rotational inertia is analogous to inertia's role in translational motion. And just like inertia, rotational inertia is an inherent property of all particles that have mass. That means every particle, every object that has mass has rotational inertia. The symbol for rotational inertia is capital I, and the SI units are kilograms times meters squared. So let's take a look at the role mass, radius, and shape play in rotational inertia. So rotational inertia increases as the mass increases. It increases as the radius increases, and it also increases as the shape causes the mass to move further away from the axis of rotation. And let's just take a look here. Here we're comparing a pipe. Okay, so a pipe's hollow in the middle. That means all of the mass of the pipe, all 5 kilograms, is concentrated out here at the very edge of the pipe. Here we have a solid rod, so the mass is distributed evenly throughout this whole circle, all 5 kilograms. So they both have the same mass and they both have the same radius, but the rotational inertia of the pipe is greater than the rotational inertia of the rod, because the shape causes the pipe's mass to be further from the axis of rotation. Here's the axis of rotation, and all the mass is hanging out here at about 0.25 meters away. Whereas in the solid rod, you do have some mass out here, 0.25 meters away from the axis of rotation, but most of the mass is closer than that. Let's look at another comparison. Here, we also have a solid rod. I know I didn't fill it in here, but this is a solid rod. It has a radius of 0.25 meters, but instead of 5 kilograms, its mass is only 2 kilograms. This rod of 5 kilograms has greater rotational inertia than this rod because it has more mass. And finally, here we have a solid rod. It has the same mass as this previous rod, but now the radius is only 0.1 meters instead of 0.25 meters. And this rod has more rotational inertia, even though it's got the same amount of mass. The reason it has more rotational inertia is because it has a larger radius, so more of the mass is distributed further away from the axis of rotation. Here, the farthest the mass is from the axis of rotation is 0.1 meters, whereas here we have quite a bit of mass that's more than 0.1 meters away from the axis of rotation. And in summary, rotational inertia is a function of how mass is distributed about the axis of rotation. And how that mass is distributed is affected by the total mass of the object, the radius of the object, but also the shape of the object. Let's look at rotational inertia quantitatively. So for a system of particles, also known as a point mass system, the inertia is equal to all these particles' mass times the radius squared, keeping in mind that radius is the distance from the axis of rotation. We add all those individual particles up. Let's take a look here. We have a 4-mass system. These 4 masses are connected by rods of negligible mass, so that means they're not going to figure into our rotational inertia calculation. The first step is to find the axis of rotation, and so this is our axis of rotation. The second step is to find the length of the lever for each mass. So this mass is 1 meter from the axis of rotation. This one is also. Down here, the masses are only 0.6 of a meter away. So now we need to find the product, mass times the lever length squared, for each mass and add them up. So here we go, 2 kilograms times 1 meter squared, plus we have another one of those, and then the two lower masses are 1 kilogram times 0.6 meters squared. We add the 4 individual rotational inertias and come up with 4.72 kilograms meters squared for the system of these 4 point masses. Now, not everything's a point mass, so let's look at a rigid body. And so when we have a rigid body, we treat it as a system of infinite point masses. So that means we're going to take the radius squared times these infinitely small masses, and we're going to add them all up. That's the limit of the sum of our particle masses as the size of those masses go to 0, which means we have an infinite number of particles. This is known as a Riemann sum, and so that leaves us with the impulse is equal to the integral of the radius squared dm. Now we do need to substitute dr for dm, and this will be different for different shapes. And this is kind of similar to what we had to do to find the center of mass for rigid bodies. For example, for a thin rod, dm is equal to m divided by L dr, where m divided by L is the rod's linear density, because capital M is the total mass of the rod and capital L is the total length of the rod. The axis of rotation will determine the limits of the integration. So let's take a look here. We have a thin rod rotating around its end. So here's the end and it's rotating about. We have all of our little masses, dm, but of course we can make them equal to m over L dx in this problem. We've laid out the rod along the x-axis, so x is replacing r. Our integral is m over L x squared dx, and our limits of integration are from 0 all the way to L. So we go ahead and solve this integral, and we find out that the rotational inertia for a thin rod rotating around its end is 1/3 its total mass times its total length squared. Now, what happens if we take this same thin rod and we rotate it around its center of mass? So we'll assume it's a uniform distribution of mass. So the center of mass is going to be right in the middle. So it's rotating around this axis. And once again, our infinitesimally small mass particles are equal to m divided by L dx. That's the linear density. Notice our limits of integration are going to be different. They're going to be from negative L over 2 to positive L over 2. And that's going to make a difference. Notice up here, it was 0 to L. Here, it's negative L over 2 to L over 2, with the axis of rotation, of course, being 0. And we go ahead and solve this, and we find out that the rotational inertia for a thin rod rotating around its center of mass is 1/12 times its total mass times its total length squared. So let's just pick a specific rod, one that has a total mass of 2 kilograms and a length of 0.5 meters. And we can go ahead and plug in our numbers for this equation up here, and we come up with 0.167 kilograms meters squared when we rotate the rod around its end. Notice when we rotate the rod around its center of mass, its rotational inertia is much less. 0.042 kilogram meters squared. In other words, it takes less effort to get this rod rotating around its center of mass than around one of its ends. And of course, the reason for that is when you rotate it around the center of the mass on either end isn't distributed that far away from the axis of rotation, compared to when we rotate around the end, then some of the mass is really far away from the axis of rotation, and that makes it harder to rotate. The parallel axis theorem is very helpful in calculating the rotational motion for an object when it's not rotating around its center of mass. And what it tells us is for any axis of rotation that is parallel to the rotational axis that runs through the center of mass, where I sub cm is the rotational inertia about the center of mass, and d is the distance between the two axes, we can find out the new rotational inertia by using this theorem. And of course we know that an object rotating through its center of mass is going to have the lowest possible rotational inertia. So you can see here, the further the axis of rotation moves from the center of mass, the larger the rotational inertia is going to be. In other words, it's going to get harder to rotate it. So let's take a look at an example. Use the parallel axis theorem to find the rotational inertia for a rod rotating about its end. So here we have our rod, and we have our axis of rotation through the center of the mass. We want to find the rotational inertia for the rotation around the end of the rod. We know that the rotational inertia through the center of mass, we solved this problem a couple minutes ago, is 1/12 ml squared. Using the parallel axis theorem, the rotational inertia around the end of the rod is going to be equal to the rotational inertia through the center of the mass plus the mass of the rod times the distance between the center of mass and the end of the rod, which of course is L/2 squared. We go ahead and finish the math, and we find out that the rotational inertia is 1/3 ml squared. And of course, that's exactly the same answer we got a few minutes ago when we solved the integral for rotation about the end of the rod. So this parallel axis theorem allows us to quickly find the rotational inertia for an axis of rotation other than the center of mass, and it allows us to do it without doing a time-consuming integration. Let's move on and look at rigid body point mass combos. And that's what we have here. We have a rigid body, and in this case we have 2 point masses, but you could have any number of point masses. And these point masses are symmetrically located away from the axis of rotation, and they both have the same mass. This does not have to be the case. The point masses could be completely distributed asymmetrically along the rigid body. In finding the total rotational inertia, we first need to find the rotational inertia for the rigid body. And of course, we know a thin rod rotating about its center of mass is 1/12 ml squared. I forgot the squared there. We plug in our numbers, and we come up with this rotational inertia for the rod. Next, we need to find the rotational inertia for the point masses. Well, we have 2 of them, but they are equal to each other because of the same radius and same mass. So we go and plug in our mass and our radius, which is the distance from the axis of rotation, and we find out that this is the rotational inertia for each of the point masses. And we go ahead and add them up. We find out that it's 0.0041 kilograms meters squared. Notice that for this system, the point masses made up the majority of the rotational inertia. Well, this wraps up rotational inertia. Let's move on to rotational kinematics. So we can use quantities to describe rotational motion that are analogous to those used to describe translational motion. First, we have angular position, and this is the position measured as an angle. And the way we do that is we have a line known as the positive x-axis, and then wherever our object is in its rotation, we draw a radius line from the origin to the object, and then the angular position is this angle created by the positive x-axis and the radius line. Its symbol is theta, and it has SI units of radians. We have angular displacement, and that's the change in the angular position, also known as how far it rotated. We can use the symbol d theta or delta theta, and the SI units are radians. We can see that we calculate this displacement as theta minus theta sub naught. In this example, theta sub naught would be 0 because the rotation started at the positive x-axis. Next, we have angular velocity. That's the rate at which the angular position changes, or we'd also say this is how fast the object's rotating or spinning. Its symbol is the Greek letter omega, and its SI units are radians per second. We calculate omega as d theta dt. Angular acceleration is the rate at which the angular velocity changes. It's also known as how fast the rotation or spinning is speeding up or slowing down. Its symbol is the Greek letter alpha. It has SI units of radians per second squared, and mathematically it is d omega dt. We can see through our definitions, our units, as well as our math definitions, these rotational kinematic quantities are very similar to their translational counterparts. Let's take a look at the relationship between our translational and rotational quantities. They are related mathematically. Displacement would be this arc length, we'll call that delta x. Our basis for relating displacement to angular displacement is the equation for the circumference of a circle. We know that the circumference is equal to pi times diameter, but because the diameter is 2 times r, we know that the circumference is equal to 2 pi r. And that gives us the relationship that the displacement is equal to the radius times the angular displacement. Let's take a look at velocity. We know that velocity is dx dt. We have a new expression for delta x, so we can plug that in there and take the derivative of this expression with respect to time. The chain rule gives us the angular displacement times dr dt plus the radius times d theta dt. But the radius is constant, so dr dt is 0, which leaves us with the relationship that the velocity is equal to the radius times the angular velocity. Similarly, we can analyze the tangential acceleration. It is dv dt. We have a new expression for velocity. We plug that into the derivative, and we take the derivative of this expression with respect to time. We're left with these two terms. Of course, dr dt is 0 because the radius is constant, and that leaves us with our final relationship that the tangential acceleration is equal to the radius times the angular acceleration. Notice that the common factor in relating all of the translational quantities to their angular counterparts is the radius or length of the lever r. Let's take a look at some rotational kinematic equations. So far I went ahead and brought up the things that we've learned about rotational kinematics. So when angular acceleration is constant, we can predict rotational motion with equations that are similar to those used to predict translational motion. And let's take a look at them. With translational motion, we have what we refer to as equation 1. The velocity is equal to the acceleration times time plus the velocity at time 0. Rotationally, we have a very similar equation. The angular velocity is equal to the angular acceleration times time plus the angular velocity at time equals 0. Equation 2. Translationally, this is one of our most often used equations, and there is a counterpart for rotational motion. The angular displacement is 1/2 the angular acceleration times time squared plus the angular velocity at time equals 0 times t. And our third translational kinematic equation has a counterpart in rotational motion. And once again, you can see the quantities here. So this equation 3 allows us to predict motion when we don't know the elapsed time. Let's take our kinematic equations and put them into action and solve some rotational problems. A torque is applied to a resting ball that causes it to spin with an angular acceleration of 5 radians per second squared. What is the ball's angular displacement after 5 seconds? We can look through here, and the equation we want to use is number 2. And so we go ahead and plug in our numbers. And we find out that after 5 seconds, the angular displacement is 62.5 radians, which is about 10 rotations. Let's look at another problem. A disk is rotating counterclockwise at 10 radians per second when a torque is applied to the disk that creates a 2 radian per second squared clockwise angular acceleration. How many rotations does it take to stop rotating? Well, here we have to remember direction-wise that counterclockwise is positive and clockwise is negative. So if we look at this, we don't know the time, so we can use equation 3. So we're going to have to rearrange it to find the angular displacement, delta theta, and we go ahead and do that. We plug in our final velocity, our initial velocity, and we divide it by 2 times our angular acceleration, remembering that the angular acceleration is in the negative direction, and that leaves us with 25 radians. Now, we weren't asked for the angular displacement, we were asked for the number of rotations, so we have to go one step further, and we know that the number of rotations is equal to the angular displacement divided by 2 pi radians per rotation. And we go ahead and do our calculation, and to 2 significant figures, there's 4 complete rotations required until this disk comes to a complete stop. Let's look at a different rotational kinematic problem. So now we're given the rotation from rest according to the function of theta equals 4t plus 3t squared. How fast is it spinning at t equals 3 seconds? Now we have to use these relationships here. We want to use omega is equal to the derivative of theta with respect to time. So we go ahead and plug in our expression for theta, take the derivative, plug in 3 seconds, and we have found out that after 3 seconds, this object is rotating at 22 radians per second. As a follow-up question, is the object undergoing uniform acceleration? Well, for this, we need to use the definition of angular acceleration, and that is d omega dt. And so we go ahead and take our equation from the previous problem for omega, plug that in and take the derivative of it with respect to time, and we get 6 radians per second, which is a constant. Hence, the acceleration is constant. This wraps up what we wanted to learn about rotational kinematics. So let's go ahead and summarize what we've learned in this podcast. First, rotational inertia is a measure of how resistant an object is to rotating. Rotational inertia is a function of mass and how that mass is distributed about the axis of rotation. We use several quantities to describe an object's rotational motion, and these quantities are similar to the quantities used for translational motion. These rotational quantities have specific mathematical definitions, which are also similar to the definitions of their translational counterparts. There are mathematical relationships between these rotational and translational quantities. We have rotational kinematic equations, which are very similar to their translational counterparts, and we can use these rotational kinematic equations to predict rotational motion. Well, this ends our podcast. I hope you found it helpful, and have a good day.